Okay, we're going to take another look here at L'Hopital's rule and see that there are some other indeterminate forms. We already know that we can use L'Hopital's rule with 0 over 0 or infinity over infinity, but let's take a look at some other limits that we might not be able to evaluate at first look. Okay, so if we have infinity over infinity, we could look at this a few different ways. So let's say that we hold the bottom constant. We have a large number there on bottom. The top is approaching infinity, and then this whole limit would approach infinity. Or if we switch this around, the top has gotten very large, but the bottom's approaching infinity. Now this would approach 0. So what we see here is when we have a limit of the form infinity over infinity, depending on which function is growing faster, the top or the bottom, we might be approaching infinity or we might be approaching 0. If they're growing at what we call the same rate, then we might approach some number in between. So we say that this is an indeterminate form because without getting a little more information, we are unable to say what this limit actually approaches. That's where we would apply L'Hopital's rule. Let's look at something with the form infinity to the power of 0. So we take a limit of a function raised to another function. The bottom function is approaching infinity, the top is approaching 0, and we ask ourselves, what is this limit approaching? Well, if we hold the base constant at 1000, so we have a large number there, the top is approaching 0, a constant raised to the power of 0 would be 1. If we let the base get really, really large, and the top is a small number, so we're going to go with 0.1, well, x approaches infinity, infinity to the power of 0.1 is still infinity. Or if we approach negative 0.1, this would approach 0. So without further information, we have a few different things this thing might be approaching. This is indeterminate. This is why we would need to apply some other method to evaluate the limit. Let's take a look at 0 to the power of infinity and go through that same thought process. So if we have the base approaching 0, so let's go with 0.1, raised to the power of a number getting larger and larger and larger. 0.1 to the power of infinity would give you 0. Negative 0.1 to the power of infinity would give you 0. And if we hold the exponent as constant as a large number and let the base approach 0, this again approaches 0. So 0 to the power of infinity, it turns out, is not indeterminate. 0 to the power of infinity is always going to be 0. Here's our list of indeterminate forms. Okay, so you don't necessarily need to memorize this list, but you do need to be able to recognize when we have a limit that can't be evaluated directly, and then we'll go through the methods that you're going to see here in the next few slides. Okay, so we have a product here. X is going towards infinity, so we have infinity times sine of 1 over x. Well, that would be sine of 0, which is 0. So this is indeterminate of the form infinity times 0. And our method for evaluating this is to turn it into a fraction so we can apply L'Hopital's rule. So x times sine of 1 over x is the same thing as sine of x divided by 1 over x. Since the limit as x goes to infinity of sine of 1 over x is 0, and the limit as x goes to infinity of 1 over x is 0, L'Hopital's rule applies. So we have the limit as x goes to infinity of sine of x over 1, or sine of 1 over x over 1 over x. Applying L'Hopital's rule, we can now cross out the negative 1 over x squared. So we have the limit as x goes to infinity of cosine of 1 over x. Well, 1 over infinity is approaching 0. Cosine of 0 is 1. So we were able to use L'Hopital's rule, but before we could do that, we had to change the way the original expression was written. We had to turn it into a fraction, and our fraction has to be either 0 over 0 or infinity over infinity in order for L'Hopital's rule to apply. Okay, now we have an expression here where we have 1 over natural log of x as x approaches 1 from the right-hand side. So that would be 1 over 0, which would be infinity, minus 1 over 0, which would be infinity. So we have infinity minus infinity. That's indeterminate. And we can turn this into a fraction by finding a common denominator. So if you multiply the left side by x minus 1 over x minus 1, multiply the right side by natural log of x over natural log of x, we get the expression shown here. And let's verify that L'Hopital's rule is going to apply. So as x approaches 1 from the right-hand side, we have 0 for the top and for the bottom. Take the derivative of the top, we get 1 minus 1 over x. Take the derivative of the bottom, you're going to have to use product rule here. And if we go ahead and simplify this down, we went and multiplied this expression by x over x to get rid of those fractions. The limit of the top is 0. The limit of the bottom is 0. So we're going to apply L'Hopital's rule again. All right, we can simplify that down. Now if we approach 1 from the right-hand side, we have 1 on top divided by natural log of 1, which is going to be 0, over 1, or 0 plus 1 plus 1, we end up with 1/2. Okay, these indeterminate forms where we have an exponent, we have sort of a special method we use to deal with this. And it's based off this rule right here that the natural log of u to the power of n is n times the natural log of u. And we can write that as natural log of u divided by 1 over n, and now we have a fraction, and we can apply L'Hopital's rule. Okay, so if we have the limit as x goes to a of a function f of x, we can take e to the natural log of the limit as x goes to a of f of x, and we've changed nothing other than the way that it looks. We can bring that limit to the outside of the natural log, and this is going to give us a method that's going to allow us to evaluate these. So let's take a look at this. X goes to infinity of x to the 1 over x. That's the form infinity to the power of 0. So this equals e to the limit as x goes to infinity of the natural log of x to the power of 1 over x. Now we're going to use our log rules to manipulate this. We can bring out the 1 over x, and that gives us the limit of natural log of x over x. As x goes to infinity, that's the form infinity over infinity. So let's just verify here. Limit as x goes to infinity of the top is infinity. Limit as x goes to infinity of the bottom is infinity. Applying L'Hopital's rule, e is unaffected. We have the derivative of natural log is 1 over x. Derivative of x is 1. That approaches 0, so we have e to the power of 0, which is 1. And this same method will work for all of those forms, 1 to infinity and 0 to the power of 0.